Yeah. Thank you. Okay. So now we will see about single qubit. So what are the primitive gates? Okay. So there are a lot of quantum gates. Okay. But all gates are implemented logically only. But in physical, most of the gates will not be there. Okay. And it will be decomposed into several primitive gates and then it will be implemented. So there are single qubit primitive gates, 2 qubit primitive gates, and 3 qubit primitive gates. Okay, we'll see all these things. So I think everybody has learned this Pauli X gate, Y gate, Z gate. Just summarizing it here. So X, Y, Z all are this Pauli X, Y, Z gate. Okay, and H is the Hadamard gate, which creates superposition. So its unitary matrix is given here. Okay. And then, yeah. So phase gate, S dagger tag, T dagger, V dagger. Okay. These are square root gate. So V is a root square gate. Okay. If you want to implement NOT gate with V gate, so 2 V gate you have to put root X into root X. Okay. So these are actually for decomposition. It is kept like this so that minimal component should be used in the actual circuit. In 2 qubit gates, C naught gate, control Z gate, swap gate, I swap gate. These are some of the gates. Okay. Single qubit gate can manipulate individual qubit. So 2 qubits. Why we need 2 qubits? Without 2 qubits, you cannot create entanglement. With single qubit, you can create superposition, but 2 qubit is very much needed for creating entanglement. And 3 qubit gates also there. Toffoli, Fredkin, and Parrish. Mostly these gates are implemented with some of the single qubit primitive gates and 2 qubit primitive gates only. Okay. So here you see the quantum cost. Okay. So here the quantum cost is 15. So 15 to 20, 5 to 6. So with ancillary it is reducing. Okay. With ancillary it is reducing. Without ancillary it is increasing. So ancillary qubits are some extra input. Okay, extra input which is just to maintain reversibility and just we will see the thing. So Pauli X gate, it is just it's like a NOT operation. So it is just a NOT operation. 0 1 1 0. So if you give 0, it become 1. If you give 1, it becomes 0. Okay. 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 So what is V gate? V gate is root X of NOT gate. Okay, of C NOT gate. So used for quantum circuit decomposition. Decomposition of Toffoli gate uses 1 to 2 qubit gates, reduce quantum cost in reversible circuit, construction universal gate with minimum gate type. Okay. So these are some of the gates. Okay. So single qubit primitive gates X, Y, Z, H, T dagger, S dagger, V dagger. This many things are there. And two qubit primitive gates C naught, swap, control Z, I swap. These many gates are there. And Toffoli, Fredrin, Parrish gates are there. Okay. So just to explain the V and V dagger because these gates will be used often. Primitive phase and square root gates. Okay. So pi by 4 rotation, pi by 2 rotation, pi rotation, rotation gate. Okay. Pauli Z gate. Okay. So Feynman gate. Okay. Richard Feynman. It is named in name of Richard Feynman. This is nothing but C naught gate. Okay. So C naught truth table. I think you might be aware. Okay. Directly we can implement and show. Let me quantum. If you have created account in IBM, then you can also just log in and see. So now two-factor authentication is there. You can use any of the authenticator apps for two-factor authentication. So I'm getting this key for logging in. Verify, verify. Platform. Okay. So just I'm showing. Okay. For example, now I'm just creating a Hadamard gate and then submitting to the real quantum computer. That process is actually transpiling. So now Hadamard gate is done. Now I am running it. Okay, I'm just choosing. some computer here. I'm running this circuit. Need at least one measurement. Okay, so we need to put a measurement here. Otherwise, in actual quantum computer, it won't run. Okay. View job detail. So the actual gate is only one. Hadamard gate I put and I measured. Okay. But during the transpiling operation, this Hadamard gate is converted into rotation gate on z-axis and then root x gate and rotation on z-axis. Okay. Pi by 2 rotation, then root x gate, that is v gate. We can call it as v gate or root x gate. Okay. So this is the gate we are telling here. Full screen. Yeah, this v gate is called root x gate. Okay, v is equal to root x. So this is how it is generated. H become this three gates. Okay, so now we will try to do this. R is it root x, R is it? Okay, poser. If I put a H gate, you just see this Q sphere. Okay, before H, it is in zero state because qubit 0 is initialized to 0. Okay, and now after applying Hadamard gate, so it becomes 0 0 and 0 1, both 50-50 probability. 0 also 50 probability, 1 also 50 probability. But when I transpile this, the actual gate is RZ gate followed by root X gate followed by RZ gate. So this is also similar operation. So 50%, 50% probability, qubit is in 0 0 and 0 1 state. So this is how it is. Actual gates are converted into primitive gates. Okay. Any doubt in this? Yeah. So Hadamard also creates the same, and these three gates also creating the same. Okay. So it's equivalent. Okay. So that's why. So we have a lot of primitive gates. Root X dagger. That is V dagger, T dagger. T is for n by n by 8. Pi by 8 actually. Pi by 4 or pi by 8. Okay. So Feynman gate. Feynman gate is just C naught gate. So through Feynman gate, you can implement AND gate also. So Feynman gate, if control and target. Okay, A is the control bit, B is the target bit. If control bit is 1, then the target bit will negate. Otherwise, it will go as it is. Okay. For example, now we are applying 0. We are applying 0 here. If you are applying 0, so 0 0 0 0 0 will go and 0 will go. No change. If you apply 0 and 1, so 1 will go as it is, that is 0 1 again. If you apply 1 0, then 1 it is going as it is, so control is 1, so 0 will become 1, that means output will be 1 1. For 1 1, 1 it is going, so 1, and it is giving control, and 1 will become 0. Okay, so this is the gate operation of Feynman gate, that is otherwise called as C0 gate. Okay. 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 So we can implement XOR operation with Feynman gate. Okay. So what is XOR operation? If the both the inputs are same, output is same. Okay. If inputs are different, output is 1. If the inputs are same, output is 0. If the inputs are different, output is 1. Okay. That is the XOR operation. So here it gives XOR. Okay. 0 0 means 0, 0 1 means 1, 1 0 means 1, 1 1 means 0. Okay. So you can implement XOR, that irreversible computing XOR gate can be replaced by Feynman gate. Feynman gate is reversible. Here the number of input is 2, here the number of input is 2. And P equal to A, this is a garbage output. You don't need this. Okay. So pass through XOR of A and B. So this is the thing. And you are interested in only Q. So you can take this, and this is garbage output kind of thing. Okay. So A is only here, the sole purpose of A is just to assist in reversibility. Feynman gate is essential for XOR gate with an extra output A to preserve reversibility. Okay. So now XOR gate we converted into reversible gate. Okay. With Feynman gate. So then double Feynman gate. In double Feynman gate, this is the logic here. So it is a 3 qubit. Okay. So it is 000000001. So this we can implement. This is with 2 XOR gate. Okay. This we will just show the implementation. So it is A to B and A to C, 2 XOR operation only. It's 3 qubit. And A to C. So now this gate is double Feynman gate. Okay. Just we will just check some of the things randomly. For example, if it is so 0 0, okay, we will just see here only. 0 0 0 becomes 0 0 0 only. So how you know this? So we just draw the barriers so that we can, that circuit handling will be easy if you put barriers. So by default, Q0 is 0, Q1 is 0, Q2 is 0. So the output is 0 0 0. Okay. Output is 0 0 0. For 001 it is 001. For 010 it is 010. For 011 it is 011. For 100 it become 111. Just we will execute this one and we'll see 100. We'll see 100. So 100 for 1, I'm just putting 1 not gate so that it become 1. See, for 100 it is all 1. So we have implemented double Feynman gate, okay, in Qiskit. Okay. So what is double Feynman gate? It is a 3 input, 3 output reversible logic gate, 2 CNOT gate. Total cost is 2. Okay. Double Feynman gate is used to fan out in reversible and information preserving way without violating reversibility, because direct fan out is not allowed. Okay. And garbage is there. So we need A into B. Okay. A XR B, and this one is garbage. Okay. So delay is there. If you want to have A, then there is no delay. If you want to have this operation result, delay is 1. If you want to have this operation also, delay is 1. Okay. So double Feynman gate for XR operation also you can use it. Okay, you can take only this and leave the other things. It become XR. Okay. So double Feynman gate can be used for copying also. Copying is fan out. Okay. So fan out is not allowed, okay, in standard reversible circuit, but you can do other way, okay, by using double Feynman gate in logical copying. Okay. So how you are doing? A is copied to Q and R, preserving reversibility. That means if you to copy A, B and C, if you put B and C to 0, then A will be there in every output. So here also A will be there. So here also A XR of 0 is A again. Here A XR of 0, it's again A. That means you are copying this input to all the output, but not through fan out operation, but logically you are doing. Okay. So for copying, we can use like this. If you set it B and Z 0, so A input will go to all 3 output. That means you are copying the A input to all the output. A is copied to Q and R. Okay. So then another gate, the Foley gate or CC not gate. This is also 3 input gate. Okay. So this gate can be implemented with a simple, it's already there. Default, it is already there. So just it is a CC not gate. Okay. Just one gate, the Foley gate, it's implemented. Okay. So here also, if you want to check anything, we can check it. So here 3 input, 3 output, quantum cost is 5. That means implementation using C naught, T dagger, H gate in fault alert. Okay, we will just execute this and we will see Toffoli gate how much in Qiskit how it is implemented. Okay, just I am setting up and running. I'm just choosing one of the quantum computer available, IBM Brisbane, and running the circuit. Okay, so I have to put the measurement. Okay, at least one measurement is should be there to run in the quantum computer. I'm just choosing it. So it is pending, it's in process. So let it go and see. One Tifoli gate is how it is implemented. See. So this is a V gate or square root of X gate, rotation gate. So mostly you see these two gates is a repeating. R is Z gate, root X gate, What other gates? ECR gate, ECR is there. ECR is just XR gate. That is CZ gate, control Z gate. RZ gate, same gate. Same gate is used. So basically, they are rotating in the Bloch sphere. They are rotating the position of the electron. Okay. So by this angle, then another angle. So like that, they are manipulating, and the information they are. So mostly it is RZ and root X and ECR. These three gates only. Okay. With these three gates only, they are implementing Hadamard, they are implementing XR, mostly everything. Okay. Composer. Okay. The Foley gate. So how to use the Foley as a AND gate? AND gate, what is the truth table for AND gate? If both the input is high, then the output is high. Okay. If both the input is high, output is high. 1 means 1. Otherwise, it is 0. So how you are implementing it with the Foley gate? So if A, B, A into B, C is equal to A, B into B. Okay. So here if you want, so here A, B, this is a dummy input. Okay. This is a ancillary bit. Okay. This is ancillary bit initialized to 0. It can be initialized to 1 or 0 based on your requirement. Okay. So now we are initializing it to 0. For example, now you see A and B. Okay. 0 and 0. Okay, so if you are having 0 here, so only for which condition it should activate? If both the inputs are 1, this is CC not gate. Okay, so here also two control bit and one target bit. Okay, CC not control target CCT. Okay, so control bit if is 1, then 0 will be negated to 1. Otherwise, always this 0 will come without any disturbance. For 0 0 also this 0 will come without any disturbance. 0 1 also this 0 will come. 1 0 also this 0 will come. For 1 1 this 0 will be negated. Okay, because two control bits are 1 and this 0 will be converted to 1. So you are satisfying the AND gate truth table. So with this you can generate the AND gate. Okay. So earlier we have seen NOT gate, AND gate. So if you put 1 here, if the ancillary bit is 1, then you will get OR operation. Okay. We will see in the next slide. So NAND gate. Okay. How you are? So similarly, if you put one negation before that, you will get the NAND truth table. That is 1 1 1 0. Okay. Okay. This is also important gate, control swap gate. Okay. You can create AND gate with control swap gate also. So this is also 3 input, 3 output reversible logic gate. Quantum cost is 5. So we can use two C naught gate, one Toffoli gate, or use C naught, T dagger, H gates. So here no direct fan out is not allowed. Garbage is depends on the context. Okay. So 0 to 2 depends on the usage. Maximum gate delay is 2. Okay. So this is the truth table for this C swap gate. Logic gates you can form using Fertrin gate. So you can form AND gate, you can form OR gate. So here, if you initialize C to 0, then it acts as a AND gate. If you initialize this C to 1, then it acts as a OR gate. Okay. OR gate is if any one of the input is high, then the output is high. Okay. So here, if it is 1, for example, if it is 1, then OR gate truth table will get. If it is 0, if the C is 0, then you will get AND gate. Okay. Parish gate, this is also 3 input, 3 output reversible gate. Quantum cost is 4, lower than the Foley. Okay. So here the quantum cost is 4. That means you can implement it with less primitive gates. So no direct fan out. Garbage output is depends on the context. Actually, it varies. Delay is 2. Okay. So one CC not gate and one C not gate. With this, you can form the Parish gate. Okay. Just we will do the Parish gate. Then let me check. If you have any doubt, how to implement swap gate. Okay. Swap gate is there. So just if you drag and you can see how it is going. Okay. So A, B, C, 3 qubits. Okay. Then this gate we have to use. Okay. B and C swap. Okay. Just put a gate and then barrier for giving input. One C not gate. I think we should put C not gate. Meeting. You can get from other. So all gates are implemented with this primitive gates only. Root X, rotation gate. Okay. So here it is CC not gate and C not gate. Okay. In this, so we have to just in this pattern we have to do, and whichever output we are interested, we have to take that from there. Okay. And building half adder circuit. In Qiskit, it is easy only. Just we have to understand. Yeah. just I will go through this one, so we can just show this later. So how to build a half adder is just, it's a 4 qubit. So between q0 to q1 one XOR gate, q1 to q2 one XOR gate, and q0 q1 q3 one CC not gate, it's a fully gate. Okay, then measurement, then you will get this half adder logic. Similarly, full adder also can be created with a two pairs gate. Okay, so here is a thing, we will implement it. I did not show. So this is how the full adder circuit is transpiled. Okay, so this ECR, what is ECR is X gate into identity gate, then CR, controlled rotation, X gate, then X gate identity gate. So this complete operation, this is nothing but C naught operation. Okay, applying Rx theta if control is 1. Okay, so ECR is nothing but it's a C naught gate only. So the major gates are root X or RZ, ECR. These gates are only used for almost all the circuits, half adder, full adder, anything. Okay, during transpilation. So this is the primitive gates. So why we are not going for 3 qubit gates is actually in implementation maximum, in the primitive gates maximum this actual gates will be 1 qubit or 2 qubit only maximum. But we have 4 qubits logical gates also, 4 qubits quantum gates also we have, but in physical it will be 1 or 2. Why 1 or 2 only means we need minimum 1 qubit for making superposition, and we need minimum 2 qubit for making for making entanglement. That's why minimum 2 qubit is needed for physical also, because this ECR, these things are created for entanglement. Okay, mainly without C naught gate you cannot create the entanglement. So minimum 2 qubit is needed for entanglement. So with the single qubit primitive gates and 2 qubit primitive gates only, most of the circuits are built physically. Okay, so each gates is decomposed. Okay, Feynman gate, Toffoli gate, whatever gate we have seen, those things are decomposed into C naught gate, T dagger gate, S dagger gate, V dagger gate, or Hadamard gate. Okay, these things are decomposed into, this is how it is, decomposition is done. Okay, okay, so just we will implement half adder and full adder. Okay, so half adder is, so I'm just creating barrier so that to give input to the q1 and q0 and q1. So first is q0 to q2, q0 to q2, q0 to q2, one C naught gate, then q1 to q2, one C naught gate, then CC naught gate, that is the Foley gate, 0 1 3, 0 1 3. So then just a barrier for giving input, otherwise the circuit will change. Barrier for all 4 qubits. Then measurement is needed. Okay, q2 is the sum, and this is the carry. Okay, so sorry, first digit sum and carry, yeah, sum and carry, yeah. q2, two classical bit is enough, because we are going to just store the sum and carry only. So 0 0 1. Okay, 0. So sum is going to the register 0, classical register 0, and carry is going to classical register 1. Okay, just we will simulate it. 0 0 0 0 means sum is 0, carry is 0 0 1. So only for this Sum is 0, carry is 1. Okay. So just we will do 0, 0 is 0. This is sum. Okay. Q2 is sum and Q3 is carry. Okay. So for 1, 0, it is 1, 0. For 0, 1, sum is 1. Sum is 1, carry is 0. Correct. Then for 1, 1, carry is 1, sum is 0. Okay. Similarly, we can do for full adder also. So here it is total 6 qubits. This sixth qubit is ancillary qubit just to make it's reversible. Okay. Otherwise, it is not needed. Just to logically, it is not needed, but for reversibility, we need this. So similarly, if some output which we are not going to use in the rest of the circuit, that is called garbage output. So these are the terms. So garbage output, delay, quantum cost, and input and number of input and number of output. So these are all the some of the terms we use. Yeah. Gate type. Okay, how many inputs, how many output that gate has. Quantum cost. Okay, so for implementing, how many primitive gates are used. So we have to use the gates which has less quantum cost and less delay, so that you can escape from the coherence time also, because coherence time is that, because that state will decohere before the, at least the coherence time should be the circuit execution time, otherwise you will not get the output. So at least till the circuit execution, that coherence should be maintained. So delay should be minimal, so that we can run through the circuit in the less coherence time. So that's why we have to choose the component very wisely for implementing these gates. Quantum cost is 5. If you are using more quantum cost, then obviously it will increase the delay also. So quantum cost also should be very minimal, and the gate delay also should be very minimal. And garbage output, anyway we need that, because for reversibility we need this, and direct fan out is not needed. It's not allowed. If you want fan out, then you have to do in different way. Okay, so extra ancillary bit you have to give, and like that you have to give. Okay. Okay, so this is a low level circuit of full ladder decomposition of the quantum circuit into very basic hardware level. It differs from computer to computer. Okay, so it differs from different computer even IBM, different computer to different computer, it will be different. And for different regid or other OEM, it will be different. How they implement, we don't know. So this is the process of transpiling. Okay, get decomposition. Okay. Okay. So how it is, this gates are how it is done. So Josephson junction for creating qubits. First we have to create the qubit. Then shunt capacitors are used. So these are some of the components used in these gates. For example, we know AND gate and OR gate, all are transistors only, emitter base collectors. So what is the basic component in the gates? So microwave pulse generators to control qubit rotation. So how you are rotating? So you are just changing the position of electron. Okay, in the atom. So how you are changing the position of electron in the atom? So you are applying a rotation gate. Okay, basically the primitive gates are rotation gate only. So just means you are rotating by some angle. Okay, for rotating, that means you are dislocating an electron from one position to another position. That means you are giving some pulse, microwave pulse to the electron, and then that amount of pulse determines in how much angle it will rotate. So for 180 degree it will be a different pulse, for 45 degree it will be a different pulse. Okay, so then you read out resonator to measure the qubit state. So you are measuring with the resonator. Okay, resonator circuit. Then you are finding the state. Okay, for result. Okay, then cryogenic refrigeration to make 15 millikelvin, so that the outside noise will not affect the position of the electron. Okay, so C naught realization is done by so control Z gate plus Hadamard gate, C naught gate. So C naught gate is done with identity gate and Hadamard gate, and C control Z gate. Okay, these are the some of the combination. Okay, so primitive gates actually for one small gate, so at least 5 6 operations are there, 5 6 primitive gates are there. So this is the internal, just how, just for understanding I just given this. So this will be the physical layout of the qubit. Okay, coupled to a resonator. This part is called a resonator. Okay, this is for measurement. This is the qubit. Okay, so here, so here seen, so VG is the control voltage source used for microwave driving. Input coupling capacitor. Okay, element of the LC resonator. So in middle section, what are that there? Okay, so this is how actually it is implemented. Okay, physical layout of the yeah, Josephson junction. This is a superconducting qubit made with Josephson junction. Okay, and capacitors. So this is a Josephson junction transform qubit core. Okay. So what is the now if you want to create a lab or anything for reversible computing, so we need the basic components. If it is a classical reversible computing, we need basic electronics components. If it is quantum reversible computing, we need those qubits. For classical reversible computer, we don't need qubits, but for quantum things, we need qubits. For classical, we need alternate electronics. It's like AND gate, OR gate, how it is implemented, like that. So we have to create a reversible logic gates, so that has to replace these components. Then it will become a universal reversible computer. So qubit preparation. This is for quantum qubit. Whenever qubit comes, it is for quantum. Gate control electronics, RF pulse, microwave source, or pulse laser to manipulate the position of the electron inside atom. Okay, or photon. So it depends. I'm just telling about the superconducting qubit. So or NMR based qubits. So you need RF pulse or microwave sources to change the position of the electron. So based on the pulse, it will rotate 180-degree or 360-degree, whatever it is. Detector and readout electronics, cryogenic and vacuum structure. This is for preserving it from the outside disturbance. Okay, and power and control softwares are needed. Okay, thank you. So yeah, we'll take up the questions. Yeah, this software can be used for research purpose. Yeah, this is actually we are running actually in the quantum computer only, cloud quantum computer in the Brisbane. Yeah. Why the quantum cost is 4 in the last slides, sir? Okay, so Toffoli gate minimum is 5 to 7 is the quantum cost. But this Perish gate actually the cost is 4 actually. So the implementation actually, that is the implementation difference. So how many primitive gates they are using? So sometimes you can write a program with 100 lines, same logic. Somebody can swapping two numbers. They can use they can swap the two numbers without using temporary variable also. So they are less. So it's a logic only. So how you are building the, how you are getting that truth table, that yeah, for input and output, for two input, what is the output? So you can rearrange and you can get with minimum cost, that means good. Universal gates are Hadamard gate, C naught gate, CC naught gate. These are all the universal gates. So that you can, like in classical, we have NAND gate, NOR gate. These are universal gates. So here, CC naught, Hadamard gate, rotation gates. These are all the universal gates. Quantum cost 5 and 4. Okay. See, quantum cost 5 and 4. See, quantum cost is 4 lower than the Foley gate. In physical implementation, actually, it is. We can check maybe. So one XR and one CC naught and C naught here. Okay, just so here quantum cost is 5. Okay, uses two C naught gate, one Tivoli gate, and uses only C naught T dagger H gate. So C naught will be 1, 2. Tivoli, one Tivoli means so Tivoli is converted into 1, 2, 3, 4 gates. Okay, and it will be 6 actually. No, no. So yeah, two C naught means here one C naught and two C naught and T dagger H. So quantum cost is 5 here. So here in preach gate it is I have to check it lower, but as per document it is lower than the Foley gate. So the implementation gates will be less, I think. So here maybe here it will be implemented less in CRT H. I think H gate may not. We can check it easily, but this will be different. This is generic term actually. These are whatever we are seeing is generic term. But here in Qiskit, if you run, that will be specific to IBM. That we cannot correlate. That will be specific to IBM. We can check the Foley gate. Just I will do, and we will take the screenshot. Then okay, I need a measurement. I need a measurement to run it. Okay, I'm just removing one more qubit is there because for that also some components will come in. Then just we'll see. How many gates are used? One, two, three. It may be different here, but yeah, we cannot count it actually. But as per literature, this period has one quantum cost less than the Tifoli gate. Yeah, we can use this software for such purpose. Yeah, yeah, coding is very much available. Coding is just you have to create the qubits in the Qiskit, then between qubit 0 to 1 apply this gate q whatever it is 1 2 or cc naught gate you can apply q 0 1 4 whatever it is. Yeah, through code it is very much possible. Can you also choose how the circuit transpiles in backend? That's what I showed, backend only. Whatever I showed is backend only. This transpiling happens in backend only. Just yeah, this thing's happening in background only. Josephson junction, as far I know, there is a two superconductor. In between some material they are keeping, but I'm not very well in that physics things. Yeah, yeah. 10 minutes is given free access. Qiskit is free only, but for 10 minutes only. Oh, okay. Okay, I have confused the symbol you are using for operation. I think one is for XOR gate, other for tensor product. Okay, so yeah, XOR actually it's a C not gate. Actually, XOR is a irreversible logic gate, but we are getting that same result from C not gate. Yeah, but yeah, in everywhere they are using for C not also they are using that symbol. Yeah. What do you mean by quantum cost? See, quantum cost is, see here, number of quantum primitive gates required to implement it. That is quantum cost. Okay. Number of quantum primitive gates required to implement the circuit. That is called quantum cost. Shall I implement 32-bit adder using this kit? 32-bit adder. Circuit may be big, but I don't know how much depth they are. Now we are just running all these basic things only. Complexity. But the practical challenge in realizing reversible logic is complexity only. For small gates also, because number of input, number of output increasing, so complexity is there. Everything is there in Qiskit. DFT, FFT, everything is there. Yeah. Complexity in terms of circuit design. I referred many IEEE papers and other things only. I checked some of the books. Actually, there is not much material in the books. Papers are there. Papers are there. FFT is already there. FFT is already there. You can get if you search some papers, you will get definitely. Okay, I mean, can we write our own custom implementation of how quantum circuit is transpiled? I'm not sure, but we can do it. Yeah. Yeah, all these designs are used in algorithms only because see, now we have irreversible computer and the gates are irreversible. Okay, number of input and number of output is not same. Okay, so we have to convert everything into reversible, that become a classical reversible only, but quantum by nature it has reversibility. Okay, so that is two different things we are dealing here. One is classical reversible computer and another is a quantum reversible computer. So in quantum reversible computer, so operations are reversible but measurement is irreversible. But in classical reversible computer, it's all are reversible. So that is only for reducing power. That is a general purpose computer. But this quantum is a special purpose. Yeah, slides will be shared. Yeah, slides will be shared. Yeah, if any journals are there, I will send along with the materials. Yeah.
Thank you so much, Anand Raman sir.
Yeah, thank you, sir.
Thank you for your time and the interaction shows that they have followed and they are, understood everything. Thank you so much, and participants also they are paying attention and large number in QT-05 the numbers are more. That's what I am feeling. And thank you all for participation and all the best for your exams. So the quiz is live, so you can start taking the quiz exam. Yeah, sir. Sir, appreciation is going on for you. Raman, sir, thank you so
Thank you,
much
sir. Thank you.
for you. Yeah. And 30 minutes in the next 32 hours, right? So please follow the schedule and try to complete. All of you, please attempt. If there are any struggles in joining, syllabus was still yesterday. Syllabus was still yesterday. Sanjay Pathak quizzes are not available. Please log into Canvas and check under quizzes. How much to score? Minimum 40% is pass mark. Of course, on 3 quizzes also we'll take an average, no problem. Don't worry. Quiz is not available. Huh? Check it now. Only after 4 o'clock only it is available. So एक बार आप share करो, Canvas login करके share. So you must not have logged in. Please check. Yeah, there is no single join code. Please follow the instructions. Anybody who is struggling, please follow the instructions on the, what do you say, given in the confirmation email. On PDF was sent how to join Canvas. There is a video was sent how to join Canvas. Please look at that. It is open, as you are able to see on your screen. Quiz 1 is available. 20 questions, 20 points. Tomorrow midnight is the deadline, July 18th. So this similar visibility will be there for a student. Show the student view. ऊपर कहीं रहेगा, देखो नीचे कहीं रहेगा, स्टूडेंट व्यू नीचे नीचे करो. हाँ, व्यू है स्टूडेंट है, देखो ऊपर. यू मिनिमाइज करो, वीडियो मिनिमाइज करो. हाँ, व्यू है स्टूडेंट, नीचे नीचे उधर. हाँ, उसको क्लिक करो. हाँ, this is how it will be visible for you, right? This is a student view. This is how it will be visible for you. So please look at this, and this is how it will be. So once you click on that, you will be able to see the questions. Okay. So you can take the quiz will come, right? आप छोड़ दो, आप quiz नहीं लेना. You have to click on take the quiz. If this is not available, please check how to log into Canvas and try to do that. If you have any friends who attended earlier courses, QT 1, 2, 3, they will be able to help you, right? Please take your quiz. Yeah. There may be a time zone issue. Please check your time zone. Please keep the time zone to be IST. Otherwise, the exam will open 5.5 hours later, right? So please go to your settings in your settings. Go to the account in the profile. आप वापस आ जाओ, वो क्लोज कर दो, स्टूडेंट व्यू क्लोज करो. नहीं, लीव स्टूडेंट. हाँ. In profile, you can check the settings. Once you click on settings, there will be a time zone. So you have to set the time zone to be New Delhi, right? So please make your changes in the profile where you have edit settings. You can go there and make the time zone setting, right? Time zone, New Delhi, Kolkata, Mumbai, Chennai, anyone you can take, no problem, or plus 5:30. Please change that. Yeah, till tomorrow night you can take. Once you start the quiz, it will be over in 30 minutes. It will be logged automatically. Please, within 30 minutes you have to save the quiz, right? Okay, till tomorrow night you can take anytime, morning or evening, you can take, no problem. Do it. But complete it by midnight, right? All the best. Thank you so much. Thank you, Anand Ram sir. Thank you, Ashok sir. I think Jaykumar sir left, and thank you so much.
Thank you, sir. Thank you very much.
We'll meet tomorrow. Yeah,
Yeah,
Anand Ram sir.
yeah. Thank you, sir. Thank you.
Right. Okay.
Okay.